Welcome to the next lecture on algebraic number theory. This is going to be primarily a review of free modules, and I want to talk a bit about why I want to give an overview of what free modules are. So basically our goal is to understand the ring of integers say O sub L as an abelian group. So possibly the most general way to state the goal of algebraic number theory is to understand these ring of integers just full stop. One way to do this is to understand it as an abelian group, or equivalently. So being basically abelian groups are exactly Z modules, or equivalently as a Z module. Okay. So basically, what does this look like? What does the group structure, the additive group structure on O sub L look like? So we'll eventually prove the following theorem. Eventually prove so we're going to prove the following statement: let L be a finite extension of Q of degree m good. Then O sub L, so what can we say about this? As a Z module, it will be a free Z module of rank M. Okay. So if the degree of the extension is M, then the ring of integers are a free Z module of rank M. Okay, so we won't be able to prove this right at the bat. We're going to have to develop some techniques. So we need to build up. So to prove this, we need to build up the machinery of traces, norms, and discriminants. Okay, which will take probably quite a few lectures. So this statement here is kind of, let me maybe, oh, in a different color. This statement here is going to be our goal for probably the next 3, 4, or 5 lectures. So anytime you're wondering why we're doing such and such, this is what you should have in mind. Okay, so what is this lecture going to look like, our lecture on free modules? Well, first we're going to start by, overview. Okay. So the first thing we're going to do is just give some definition of what a free module is. I guess a finitely generated free module. Definition of finitely generated free modules. Okay. Second thing, it will be useful probably much later, probably like 4 or 5 lectures away. So we're going to give some criterion for when a collection of elements form a basis for a free module. So essentially, once we've proven this theorem, an important question will then be, how do I find a basis for this O sub L as a free Z module? So how can I describe, how can I give a basis of this thing? And this criterion, along with some later criterions, will be useful in determining whether my collection of elements is a basis. And the third one is kind of like a useful lemma that will come up later. So in the case that we're working over Z, so for example, this is the case when I'm worried about Z. In the case where we're working over Z, we are going to prove a formula for the index so the index of n in a free module M of a module n generated by n linearly independent elements in a free module M. So unlike in the case of, like, say, vector spaces, where linear independence is equivalent to spanning, so n linear, I guess, sorry, maybe that's a little wrong to say. If I have n elements of a vector space of dimension n, they span if and only if they're linearly independent. That doesn't quite happen in over Z. It can happen that I have n linearly independent elements in a free module of rank n. So I should add this. I can have n linearly independent elements in a free module of rank n that don't actually span, so that this index isn't 1, it's less, or it's bigger than 1. Okay, so these are the 3 main goals that we're going to try to get done in this lecture. So let's go ahead and start with the definition. This is 16.1. Definition. Okay, so I'm going to let M be an A module. For ring A. We say E1 through En. So some collection of elements of M is a basis for M. If 2 conditions hold. I guess this should be in red, so let me go ahead and is a basis for M if 2 conditions hold. 1, so this is a linear independence condition. So if the sum of these guys, if an a linear combination of these E sub i's are 0, then each a sub I actually had to be 0. the first condition. The second condition is a spanning condition. M is generated by this collection. Okay. So a basis is basically a linearly independent spanning set, and if M has a basis of n elements, then we say M is a free module of rank n over A. Okay, so essentially, like, I guess one, like, the quintessential example of this is every vector space is always a free module over the field. So every vector space has a basis, and the dimension is the rank. Okay. So next, we're going to state a series of propositions which help us understand free modules a little bit better. So 16.2. This is a proposition. I guess I should say, in a way, free modules are kind of like the simplest modules because in a lot of ways they behave very similar to vector spaces, and vector spaces are something we understand. So if you know something's a free module, that's a very good thing. And this proposition kind of like classifies what all your free modules look like up to isomorphism. So I'm going to let M be an A module, let's say with basis, or sorry, I actually want to state this as an if and only if. So let M be an A module, a collection so let's say I have a set of elements here, and I'm wondering, is this a basis? Well, this collection is a basis if and only if the following map is an isomorphism. The map for V from A to the N to M, since delta sub I to E sub I, so where delta sub I is 1 in the ith component, and 0 elsewhere. Okay. If and only if this map is an isomorphism. Okay, so I'm not going to prove this statement. I guess maybe the proof, I'll leave it as an exercise. It's not too bad. You essentially just use the definition of what it means for this thing to be a basis. And what we get out of this is that if I'm a free module of rank n, then I'm automatically isomorphism. I should tell you what this isomorphism is as A modules, sorry. It's an isomorphism of A modules. Okay. So the proof shouldn't be too bad if you understand this definition, and working through it can be useful to help you see like how to use these definitions. Okay. So then the next proposition will be another thing that looks hopefully familiar from linear algebra. And this will tell you basically if I'm working in a free module already, how do I tell if a collection of elements is a basis? So I'm going to start with a basis. So let this guy be a basis. And I'm going to let's suppose I have another collection of elements. M be any elements. Then F1 through Fn is invertible if and only if, sorry, what am I saying here? I skipped a line. Doesn't make sense to ask this to be invertible. Why? Okay, this collection is a basis if and only if only if the change of variable matrix B equals B sub ij is invertible. Now, what is the change of variable matrix, you ask? Well, here F sub I is the sum over Bij Ej. So essentially it's the matrix where if you multiply by each Ei you get the Fi. And the proof, you can prove this basically using linear algebra, or like the same technique you would use from linear algebra. It's kind of like maybe a more clever way proof. Basically we have the following commutative diagram. Okay. Where on one side I have M, and on the other side I have AN. Okay, and this matrix B acts as, what do I want to say here? M. So, on the left and on the right, I have essentially these maps up here. So, if this is the one corresponding to E and this is the one corresponding to F, maybe they should be like inverses or something like this. Maybe I'll just make the arrows go the other way. Okay. Okay, and then you ask, like, okay, what is this top map here? The top map sends EI to F sub I. Okay, and if EI is a basis, this will be a well-defined morphism. And okay, for Fi to be a basis, I need so I guess first you need to check, okay, that this actually commutes. So check the diagram commutes. Okay, so I need to start with, like, say, delta I here. It would map to like b delta I and so on and so forth. So you work through the details of checking this diagram commutes. Then these things are basis if and only if for phi sub f is an isomorphism okay. What do I want to say here? One second, I'm thinking about how this argument would work, if it actually does work. Okay, so I want to say that I can go around, so if B is invertible, then I can go around backwards. But I also kind of need to know this map is invertible. I think maybe this doesn't work. Well, I think it's easy enough to well, I guess maybe I would just say you could prove this from scratch, but okay, so there are some pieces, some steps that you need to prove. So if f is a basis, prove that this top map is invertible. EI maps to FI is invertible, or is an isomorphism. So that this map B, given by the matrix B, is the same as first do bar phi sub E, then do this top map, which I'll call, I don't know, psi. Then do psi. Then do bar phi sub F inverse. Okay, is invertible. It's a composition of a bunch of invertible maps. And if B is invertible, then if B is invertible, if I can go backwards, what does that mean? Oh, if B is invertible, then you kind of have to resort back to this linear algebra proof, I think. So maybe this only, well, as far as I can tell right now, this only really works in one direction. And use that EI is in the pre-module generated by Fn. Okay, so if they're invertible, then you can show this. and show linear independence of these guys by hand. Okay, so you have to be a little more careful. Basically, if you had a linear combination of these that were 0, you could apply B and then get a linear combination of the EIs, which were 0, and so on and so forth. Okay. So, what I want to say, I'm not going to work through this proof in detail. Review linear algebra. It's more or less what I want to say. Okay, so the next proposition is again something that's going to require a construction from linear algebra, which is probably not super familiar, and I'm not going to go through in detail. So the proposition is this: a matrix Aij, an n by n matrix with entries in A, is invertible if and only if the determinant is a unit. Okay, so remember in the case of fields, you just need the determinant to be non-zero. That's because every non-zero element in a field is a unit. In the case of rings, I really need this to be a unit in my ring. And I'm not going to prove it, but I'll tell you the key thing that you need to prove this. You construct something called the adjugate. So you need to construct this adjugate matrix, which there's a formula for that you can probably find on Wikipedia. It's complicated. You usually call this like the adjugate adj Aij. This matrix, the important property this thing satisfies, this has the property so what is important about this? Basically, when I multiply a matrix by the adjugate, I get the determinant. So it doesn't matter which order I multiply them in. I get the determinant of Aij, my matrix, times the identity, the n by n identity matrix. Okay. So basically, one direction of this proposition is easy. If I'm invertible, then since the determinant is multiplicative, the determinant of this matrix has to be a unit. If the determinant is a unit, then this matrix is invertible, which means that Aij times this thing, Aij times another matrix is invertible, which means that Aij is invertible. Okay. So this proposition is useful because it kind of tells you, like, okay, this tells you that in order to check my elementary basis, I just need to check if a matrix is invertible. This tells you to check if a matrix is invertible, I just have to compute one constant, the determinant. Okay. The final thing I want to prove, so this is the third thing on my list of overviews, it's probably the most difficult to prove thing that we're going to talk about today. This is 16.5 proposition. So we're going to let our ring be Z and M be a free Z module of rank M. Okay, and let's say we have linearly independent elements F1 through Fm be linearly independent. So the question is independent. Question is essentially like, okay, are these a basis, and if not, how big is the module they generate? So how much do they span in a vague sense? So we're gonna let n be the module they generate. N is gonna be zf1 plus zfn. Okay, so this is the module generated by f1 through fn, and let's say this guy is a basis. It's a basis. Construct the matrix B above. So this is the change of variables matrix from E to F. Okay, and the claim is that the index of this module, the index of n and m, is exactly the determinant of the change of variable matrix. Okay, so what are we saying here? I guess there are a couple of things we're saying. One is, so let's compare this to 16.4 and 16.3 that we, sorry, there should be an absolute value here, that we figured out before. So 16.4 says a matrix is invertible if and only if the determinant is a unit. Okay, so in Z this means that this determinant is either plus or minus 1, so this matrix B is invertible if and only if the matrix is plus or minus 1, or the determinant of the matrix is plus or minus 1, and the matrix is invertible if and only if these FIs form a basis by 16.3. So this kind of basically we already know one case of this. So in the case that this determinant is plus or minus 1, then this equality says that n equals m, so this index is 1, if and only if B is invertible, which we already knew because if B is invertible, then these guys are a basis, and if these guys are a basis, then B is invertible, and so the determinant has to be plus or minus 1 and so on. Okay, so we already knew the case when the determinant was plus or minus 1. The other case is a little bit more work. So you need basically to construct a specific basis. You can't just use this EI, you need to use something more clever. So the first I claim we can choose a basis. EI prime such that for some integers mi, if I define fi prime as mi times ei prime, then these guys form a basis. And form a basis for n. Okay, so what is this saying? This is saying essentially that, well, there are a couple different ways to look at it. One way is to say, okay, if I shift my view of M a little bit, so I change the basis that I am working with, then N is like essentially taking each one of these basis elements and just scaling it. Another way to look at this is we're kind of like trying to diagonalize this matrix B. So what do I mean by this? So this is equivalent to finding matrices, invertible matrices, so not just any matrices, and by n matrices x and y such that let's see here, such that x, b, y is diagonal. Okay, so how do I come to understand how this equivalence? Essentially, so you should think of y as basically a change of basis for M. So this is saying, okay, take my EIs and do some invertible transformation to get me a new collection of elements EI prime, or sorry, maybe I want flip that around. So y takes the basis here, sorry, here, E1 prime to En prime. It's going to be y times y inverse, sorry. Yeah, this is kind of confusing to me if you can't tell. So essentially, y is a change of basis matrix on M, which takes my EI primes to my EIs. Then B takes my EIs to my FIs, and X takes my FIs to my FI primes. Okay. So essentially with this matrix, I'm plugging in EIs, or I'm plugging in EI primes and getting FI primes out. I realize this is fairly confusing. I'm trying to think of maybe a better way I can explain what's going on here. So if basically, I don't really need both directions of this if and only if. I only really need one direction. So if x by is diagonal, then how do I define these EI primes? So EI prime will be essentially the sum over y sub I, y sub j, e sub j. And this should be, well, this is a little abusive notation. When I write this inverse, I don't mean the actual like multiplicative inverse of this number. I mean the ijth element of the inverse. So maybe I can be more clever with how I write that. Maybe I'll write y inverse sub ij. Okay. And similarly, f sub I prime will be, so instead of the inverse, it'll just be the regular x sub ij f sub j. Okay. And then these will, you can check that these bases actually satisfy the conditions. So such that, you know, mi times ei prime equals fi prime. Let's say and if, so let's say the diagonal matrix here xby equals m1 through mn, then these bases will satisfy the conditions. So they satisfy the necessary conditions of the claim. Okay, so what is going on here? I guess, so first I'm basically saying I can choose some nice bases for m and n that will make this problem a lot easier. So how do I know that I can always diagonalize this? I'm not going to prove this. It's something where if you've seen the proof of something like the classification theorem for finitely generated modules over a principal ideal domain, then you've seen this before. If not, you probably haven't seen this before. All I'll say is see the Wikipedia page for something called Smith normal form. To see why this is possible. Why I can find such x and y. Okay. So how do we finish up this proof here? Okay. Let's say xby equals d, which is m1 n for 0. Okay. If this is the case, then when I take determinants, so this is going to be determinant of x, determinant of b, determinant of y. Okay, so I guess on the left this will be the determinant of d. So this will be the product of the mi's, which is the determinant of d. Okay, on the right. So thinking about this, these are both units, right? In z. So these are in the units in z. Okay, and so the only units in z are plus or minus 1. So this is plus or minus the determinant of b. Thus, okay, the product of these mi's absolute value of the product of these mi's is equal to that absolute value of the determinant of B. Okay, so I claim now, that this product of the mi's is also equal to the index, the desired index. Okay, and the way we're going to understand this is essentially through a sequence of isomorphisms. So we have m mod n, it's isomorphic. So it's going to be isomorphic to z to the n modulo m1z1 or m1z cross m2z cross mnz. Okay, so if you want to understand where this isomorphism coming from, this is essentially the isomorphism coming from D. So you're going to send EI prime plus N, and this is going to map to delta to the I plus M1Z cross MNZ. Okay, and this is isomorphic to Z mod M1Z cross Z mod MNZ. Okay, so essentially I can split up this quotient of products into a product of quotients. And you can, I think, you can probably use the Chinese remainder theorem here, but you can probably just do something like this. Honestly, you can probably just write this delta sub I, where this is 1 in the ith component now, 1 in z mod m sub I z, and 0 elsewhere. Okay. So you can check. So once you check these are valid isomorphisms. And then what do we see? Then, well, the index m and n, this is the size of the quotient. All these isomorphisms are going to preserve this size. So this will be the size of z mod m1z times c mod m2z, which is exactly what we wanted, which is the size of the quotient, or the size of the product of these guys, okay, which we just saw was the same as the absolute value of the determinant of B. Okay, so the key here, well, there are a couple ways to look at it. One way to say is we basically chose good bases for m and n. The key reason we could do this was the Smith normal form, or the structure theorem for finitely generated modules over a principal ideal domain. Okay. So this will end up being useful when it comes time to decide whether a collection of elements is a basis or not. Okay, so that wraps up this lecture. Next time we'll start looking at traces and norms, and once we've worked through that stuff, then we can work on determinants and finally prove our big result.